All right, welcome everyone to today's Explainer. I am absolutely thrilled you're here because today we're looking at something that honestly feels like it's pulled straight out of science fiction, but it's happening right now. We are unpacking Microsoft's recently unveiled Majorana 1 chip. Look, this isn't just another incremental tech update. It's a fundamental promise to solve the quantum computing industry's absolute biggest roadblock. By the end of this Explainer, you're going to see exactly how a completely new state of matter might just unlock the true quantum age. To really grasp why this is such a massive deal, I want you to hold this ratio in your mind: 1,000 to 1. In traditional superconducting quantum systems, the kind being built by the incredible teams at other major tech companies, you need over 1,000 physical qubits to create just one single, reliable, logical qubit. Why? Because of massive, persistent error rates. It's literally like needing 1,000 spare tires just to drive your car down the block. So that leads us to a pretty fascinating question. What if the quantum building blocks themselves were inherently immune to errors? Right now, we're stuck in what physicists call the NISQ era. That stands for the Noisy Intermediate Scale Quantum Era. And the fatal flaw of the NISQ era? Decoherence. Current qubits are so incredibly fragile that the slightest thermal fluctuation or electromagnetic noise completely destroys the information they hold. But what if we could design a qubit that naturally protects itself? Okay, let's dive into this, because this quote from Microsoft technical fellow Chetan Nayak perfectly frames their radical approach. Instead of trying to patch up a leaky boat with massive error correction software, Microsoft went all the way back to the drawing board to invent the transistor for the quantum age. They decided to build a better, inherently protected fundamental building block right from the ground up. Here is our agenda for today. We'll cover 1. The quantum error problem. 2. Meet the Majorana 1. 3. Inside topological qubits. 4. Scaling to 1,000,000. 5. Real-world applications. And 6. The road ahead. Section 1. The quantum error problem. Breaking the NISQ bottleneck. To really understand why we're totally bottlenecked in this NISQ era, you just have to look at today's traditional qubits. I'm talking about the superconducting and trapped ion systems used by companies like IBM and Google. They have some severe limitations. We're talking agonizingly short coherence times and high base error rates, around 0.1 to 1% per gate operation. Plus, they are extremely sensitive to environmental noise. To compensate for all that, scientists are forced to use massive error correction overheads, taking thousands of physical qubits to do the job of one. And that is the high-stakes problem Microsoft set out to solve. Section 2. Meet the Majorana 1. The 20-year gamble. Now, what's really interesting about this slide is the sheer scale of Microsoft's high-risk, high-reward scientific bet. This chip is the culmination of a 20-year gamble to completely bypass traditional qubits. The secret? It lies in something called a Majorana Zero Mode, or MZM. Now, don't let the terminology intimidate you. Essentially, MZMs are exotic quasi-particles that encode quantum information non-locally. Just imagine splitting a piece of secret information and hiding the halves in two entirely different safes. A localized noise event, like a tiny bit of heat or electromagnetic interference, can't destroy the information because it only hits one part of the system. This provides intrinsic topological protection. And hey, this isn't just theoretical posturing. The strategic and national security importance of this breakthrough is absolutely massive. In fact, Microsoft is one of only 2 companies invited to the final phase of DARPA's Underexplored Systems for Utilization Scale Quantum Computing program. That is profound validation from the highest levels that topological qubits could actually be the fastest path to a genuinely useful quantum computer. Section 3. Inside topological qubits. Engineering a new state of matter. And this brilliantly illustrates exactly how you build this new state of matter. Let's look under the hood of a Majorana nanowire. Notice the specific materials at play here. At the center, you have a high-mobility indium arsenide nanowire core. That core is then coated with an epitaxial aluminum superconducting shell. When you marry this very specific semiconductor with a superconductor at extreme cold, you actually coax these exotic Majorana quasi-particles into existence right at the ends of the wire. The crazy part? The fabrication process is literally done atom by atom. First, they grow the indium arsenide core via molecular beam epitaxy. Next, they coat it with that aluminum shell. Then, using electron beam lithography, they carve these networks into H shapes, which they call H-tiles.
Each H-tile encodes one logical qubit across 4 Majораnas. What's revolutionary here is that they can control and measure these qubits digitally via voltage pulses using those underlying gold gates. It's a massive leap forward in controllability.
Now, because these H-tiles can be connected, they can be laid out perfectly like tiles on a floor to form this error correction array architecture. To manage this massive array, Microsoft uses cryogenic CMOS drivers that supply digital voltage pulses. Oh, and the kicker? This is all happening inside a dilution refrigerator at 20 millikelvin. To put that into perspective, that is significantly colder than outer space.
Section 4. Scaling to 1,000,000, the footprint advantage.
So the crucial point is, remember that 1,000 to 1 ratio I asked you to hold on to earlier? Well, notice the based error comparison here. Because topological qubits have intrinsic passive error protection, Microsoft estimates they only need about 100 physical MZMs to create one perfectly reliable logical qubit. Meanwhile, competitors using active correction need upwards of 1,000. This means while others might need a computer the size of an airplane hangar to reach 1,000,000 qubits, Microsoft's architecture provides a clear path to fit 1,000,000 qubits on a chip you can hold right in the palm of your hand.
Section 5. Real-world applications. Designing the future. So why does reaching 1,000,000 qubits actually matter so much to us? Well, because a fault-tolerant quantum computer isn't just a faster laptop. It processes the universe differently. It can execute Shor's algorithm to break 2048-bit RSA encryption, which is going to force a global shift to post-quantum cryptography. On the humanitarian side, it could perfectly simulate complex chemistry to design self-healing materials for our crumbling infrastructure. It could discover exact catalysts to break down the world's microplastics. It could optimize enzymes to boost soil fertility in harsh climates and literally help eradicate global hunger. These are tasks that are mathematically impossible for today's classical computers to ever calculate accurately. I absolutely love this quote from Matthias Scheuer. The ultimate vision here is combining quantum with AI. Instead of years and years of trial and error in a laboratory, you could use plain language to ask an AI for a new, non-toxic material with specific properties. And the quantum computer, understanding the exact laws of quantum mechanics, just gives you the perfect recipe on the very first try. Section 6. The road ahead. Hype versus reality.
Okay, as wildly exciting as all this is, we do need to take a collective breath and balance the vision with some grounded engineering reality. Microsoft has laid out an incredibly ambitious timeline. Right now, in 2025, they have 8 topological qubits on a chip. By 2028, they project having pilot modules with 5,000 logical qubits. And by the 2032 to 2035 timeframe, they aim to achieve the Holy Grail, full million-qubit fault-tolerant systems capable of tackling those massive industrial problems we were just talking about.
You can see the scale of the transition we're in right now, and it is monumental. We are moving from single qubit benchmarking and pre-error-corrected processors to massive error-corrected surface code arrays. But getting to that final stage, that is a colossal task.
Let's move to and see how this builds, because this really highlights the severe engineering hurdles that still remain. Microsoft has to overcome things like quasi-particle poisoning, where stray particles come in and just ruin the quantum state. They have to perfectly master materials disorder at the atomic level. That means they'll likely need to transition to highly complex extreme ultraviolet lithography just to get sub-5 nanometer uniformity. And on top of all that, wiring up 1,000,000 qubits inside a cryogenic freezer requires managing over 1,000,000 control lines without leaking any heat. To keep us perfectly grounded, technology analyst Olivier Ezrati provided this really sobering TLDR assessment of the Majorana 1. He said, best case scenario, it will require many years, if not decades, and a lot of work. Alternate scenario, it does not work at all, or at least it's too complicated. We are definitely watching scientific history unfold, but it is an incredibly steep mountain to climb. So what does this all mean? Microsoft has unquestionably proven that Majorana particles can be created and controlled, effectively creating a completely new state of matter. But will these topological qubits be the ultimate key that scales up and unlocks the quantum age? Or will the engineering hurdles prove it to be just an impossibly elegant theory? It is going to be absolutely fascinating to watch this space. Keep learning, keep questioning, and thank you so much for exploring with me today.